Hi guys, welcome back to the channel. Today, let's discuss about sizing in current mirrors. If you haven't already checked out my previous video of current mirror where I've spoken about just a basic current mirror introduction to the entire concept of current mirror, please do check it out. You can find it linked above and I'll also link it in the description. Usually in current mirrors, the same length is used across the transistor and the current is controlled by manipulating the width. This is done to minimize errors due to the side diffusion of source and drain areas. What is side diffusion? To understand side diffusion, we need to look at the physical manufacturing process of a MOSFET. Now let's take an NMOS. So it has a P substrate, and if this is the gate, the heavily doped source and the drain region are formed by a process called ion implanter. So it's basically atoms are placed into the silicon at high speed. So they are like shot into the silicon substrate at very high speeds. However, this completely wrecks the crystal structure. To undo this, the next step is something called thermal annealing. Here is where the side diffusion happens. When things get that hot, atoms get very energetic. This is similar to what happens when we bake a chocolate chip cookie. So the structure is kind of intact, and when we put it in the oven and when it bakes, it kind of spreads across, right? So this is what happens when the MOSFET is subjected to thermal annealing, and in high temperatures, this structure of source and drain region kind of diffuses. So it kind of becomes like something like this. So it diffuses underneath the gate area. This is why the effective length is given as the drawn length minus twice the lateral diffusion distance of the dopant under the gate on either side. I mean on one side. So the L drawn is the length that we actually input inside. For example, like EDA tools like Cadence. This is like the length that is used by engineers when they make the layout. Let's consider a case where I want the output current to be half of the reference current. And we know the formula for a simple current mirror can be given as I out is equal to I reference divided by W by L of the second MOSFET and W by L of the first MOSFET. So the second MOSFET being the MOSFET into which the I out flows. So let's try to scale the length. Suppose I want the output current to be half of Iref, then if I try to scale the length, the formula can be rewritten something like this. W by L of 2 divided by W by L of 1. If I keep the widths constant, it should be half of L1 divided by L2. So according to this formula, I can just double the length of MOSFET 2, but that will not work because let's try to plug in this effective length formula into this equation. We get I out by I reference is equal to L1 drawn minus 2LD divided by twice of L2 drawn minus 2LD. So the drawn length is the one that we input in softwares like Cadence. And you can clearly see that the length is not actually doubled uh, as per our requirement. This is not equal to L1 divided by twice of L2. This is why we keep the length of the MOSFETs constant and we try to manipulate the current by changing the width of the MOSFET. However, manipulating the width also comes with its own drawbacks because the corners of the gray gate are kind of poorly defined. So when we double the drawn width, the actual width doesn't necessarily gets doubled, but still it's better than changing the length of the MOSFET. So to get a perfect scaling in current mirrors, we rely on a concept called unit transistors. Now let's take the same case where I want to generate an output current that is equal to half the reference current. I can actually generate this in this way too. This is our reference current, IREF, and this would be our diode connected transistor. Now each of this branch carries a current of IREF by 2. Now I can copy this to our output device, and this branch would have a current of IREF by 2. These transistors are called parallel transistors, and we can set this using a setting called multipliers in Cadence. So let's take another case where I want to generate an output current that is twice the reference current. Then I can generate it by, let me just copy this. I can just generate that by actually connecting transistors, four transistors in parallel. So all the source terminals are grounded, all the drains are connected. This will have an effective current of 2 IREF. Now we generate an output current that is twice the reference current. However, the above approach requires a large number of unit transistors if many different current must be generated. It is possible to reduce the number of unit transistor used by actually using series transistors. Now I can use this approach to generate the same output currents, one output current being the half the reference current, and another output current of twice the reference current. Let's see the structure. Now this is the diode connected transistor from which the currents are copied. Now let's see what the current here is after I connect. Now if you calculate and see, actually the effective current through this branch would be twice the reference current, this being the reference current, and the effective current through this branch would be half the reference current. And these two transistors are in series. Thank you so much for watching this video. Don't forget to subscribe and see you guys in the next video. Bye.